Okay, so let's continue. So unlike Scala, Python has different behavior regarding assignments and reassignments. So the first thing you'll notice that's interesting about Python is you can reassign different values to variable names, and these can be of different types actually. So so here I'm basically assigning A1, and then you can ask what is the value of A right now and what type is it right now. That's what this print statement is doing. And then I can say A is 1/3, and so I'm reassigning A to type rational. So remember in Scala you couldn't do any of this, right? Well, if it was val, you couldn't reassign at all, but it was a variable, var, it had to be type specific and reassign. So you lose a lot of this kind of type safety that Scala has in Python, but it gives a lot of convenience as well. Yeah, so here are just some examples. Assign the value 2 to variable name x. Right. So let's do this. X equals 2. And I'm going to assign 3 to y. And then on the third line, I'm going to put an expression x plus y. Right, so I only see my output x plus 5, y is 5. So if I say x equals 4 and do x plus y, I'm able to get the reassigned value of x in my expression. So strings are our next main stopping point. So my str is equal to this double-quoted string. This is a string. And so when I ask for what my str is, I get this string in single quote. That's the Python way of showing us a string. And then I can ask what is the type. Type is str for string. So you can also do this. You can enclose the string by single quote, and it's still a string. Or you can enclose a string in triple quotes, and it's still a string. Okay, so this is quite handy if you have like other quotes, double quotes inside the expression, or usually you write your help comments for functions using these triple quoted strings. This is usually called a doc string. So you see, it can handle a double quoted string within the triple single quoted string. Yeah. So now we want to get into a little bit into Unicode strings and ask what do you call it? Say Chinese characters or some other Swedish characters that are non-ASCII. So yeah, so let's look at this. You want to understand the main difference between ASCII strings and UTF or Unicode encoded strings. So I'm going to let you read this. I basically read this tutorial, and then I kind of wrote this for us. So let's say I want to assign this hi cat. This is a Chinese character for cat. Right. So each letter is encoded by 1 byte, which is 8 bits. Right. and then it's followed by this Chinese character for cat. But the Chinese character for cat actually needs 3 bytes to hold it. Right? So now we're entering this land of characters that are not just 8 bits or 1 byte. Right? So if I just put hi cat and ask what is the type, it'll say it's a string. And then I ask what's the length of x. So this is a sequence of 5 hexadecimal numbers, each requiring a byte to represent it, right? So it makes sense. 3 Chinese characters for the cat is 3, and then H and I are 2, so it's total length 5. So then I can disclose x by only showing the hexadecimal numbers. Right. So hi is there, and then my cat is basically the hexadecimal numbers E7, 8C, and AB. Okay, so but then if I say print text, it'll print in this way, and then so what we generally want to do is we want to decode x and then make sure it's converted to a sequence of Unicode characters, UTF-8. So then I can ask what is the type of y. So then it'll give me it's of type Unicode rather than of type string, right? So now I can ask what's the length of y, and it automatically gives me length 3, right? So now we have a Unicode string of length 3, where the third element is the Chinese cat character for cat. Okay. So now disclosing y shows us the 2 ASCII characters H and I and the Chinese character cat, and it'll correspond to this particular entry in the UTF-8 table. Yeah, so there is a little bit of magic on how UTF-8 finds the new characters. There's some ordering to these elements. Okay, so yeah, so it has so elements that need more bytes are placed in a certain order, so it can figure out what character it is. Okay, so yeah, and then once again, print y will give us what we want. So now, not sure, question REPR works. Okay, that works. That gives us a docstring. So REPR is a function that takes an object, returns a string. It returns the canonical string representation of the object. Okay. So if I do print REPRY, I'm going to get my ASCII characters are shown as they are, and then the other Chinese character is this Unicode thing, and then if I do REPR of y decode Unicode escape, if I do this, then I will start seeing what I'm usually after. So I kind of did all this because I was doing some text processing on some other language for you guys later, and then I ran into, oh my god, it's all this stuff I need to know, right? So it's mainly there because if you start processing text from different languages and so on, you need these basic things about Unicode strings and how to decode them and escape and display. So here is a little book called Pride and Prejudice. So it's part of this Project Gutenberg. So let's do our first little data analysis. So this is actually about 57,000 free ebooks. So I think books before 1920 or 1913 or something are in the public domain, right? So they can actually be used by anyone. And I went to this website and I looked at the most downloaded book. So this one has 39,859 downloads. So I said, okay, let's go and look at this book everyone's downloading. And I went to plain text UTF-8 encoding. And so this is actually the entire UTF-8 encoded text of the whole book. Okay, so we're just grabbing this and playing with it next. So what we have here is an import statement. So from URL lib, which is a Python library, we're importing everything. And then I create a variable called Pride and Prejudice. And I don't have to pay too much attention to it. But there's no magic here. It's just exactly that URL that I was looking at. I put the URL as a string there, and then I ask it to .read. And so it'll download it and read it, and then I ask it to decode using UTF-8. So that's the reason for the tutorial upstairs. And then I'm basically just showing the first 1,000 raw characters of this downloaded and opened text. Okay, so this should just work for people. Let's try it. Okay. So is everyone able to go grab this book and see the first 1,000? Okay. So, okay, so if I ask what's the type of Pride and Prejudice raw, it's Unicode. And I can ask what's the length of this. It's 717,000 lines. So next we're going to show how trivial it is to read all the chapters as follows. So we're going to use regular expressions via the RE library. This is the Python's regular expression library, right? And so what we're going to do is substitute all occurrences of white space characters, either one or more consecutive white space or end of line or tabs with just a single white space. So we remove all that structural information. Then we will split it by chapter, because if you noticed that URL I showed you, each chapter began with this word called chapter, right? With a capital C. So it was chapter 1, chapter something. So we're going to break this whole text by chapter. Right? So it's basically the splitting step, and then we're going to print the first 100 characters in each of the first 10 chapters. Okay. So that's what this is doing. Right now, you don't have to fully understand this. We'll go through for loops and everything very quickly in a minute. But basically, that's all that's going on here. And so these are the first line of. Where's 61? I thought there should be only 10. Oh, first 100 characters in each of the first 10 chapters. What am I doing? Oh, I guess I'm going through all the chapters, right? So if I did 1 through 10 here, probably closer to what okay. So you'll see all these slices and stuff. But yeah, this is just to say that Unicodes are useful, and we can just grab a bunch of stuff and start doing some analysis easily. Okay, this is a very important gotcha in Python. I really don't like Python for this reason, but something to be aware of, especially if you come from C or some other place like this. So what we're going to do is, here I'm assigning 3 to x. So what Python does, or SageMath does, is it chooses a memory location for x and saves the integer value 3 in that location. Right? Now the second assignment here, y equals x. Here what's going to happen is a bit more interesting. So instead of finding another location for the variable y and copying the value of 3 to it, Python does something else, right? So it says, okay, since both variables will have the same value after the assignment, Python will just simply let y point to the memory location of x. This is a very Python behavior, okay? So then that means, when you print x and y, x will be 3 and y will be 3 as well, but y is actually just pointing to the location of x. So then if you do this third assignment where y equals 2, so what will happen now is x will not be changed to 2, right? Because remember, y was pointing to the memory address of x, but then you change the value of y. So now it doesn't change the value for x, right? It will say, oh, okay, now y is a separate guy, so it'll make y its own thing, its own memory address, basically, and assign 2 to it. I don't know why they do this, but apparently it's a feature.
And what happens if you say, like, y equals 2 times x? It also assigns the same?
I think so. I think we can try it. I mean, so let me try to understand this for sure. Okay, so yeah. So y gets its own. So if instead of this, okay, before we do that experiment, let's just. I want to remind myself of this ID thing. So the way you keep track of who's who is using this ID operator. So every instance has an ID, right? So it's a unique integer within the program that tells us exactly where things are, sort of unique memory. So here is how we can basically do the same thing, right? So exactly the same as before, but now I'm printing both x's value and its ID. See, so initially when x is 3, its ID was this number. And then the next thing is y is 3. And see, y's ID is exactly the same as x's, like we said. And then now you see it has changed the ID for y, because y is... So you wanted to do this, right? You want to do y equals 2 times x or something? Okay. Yeah, so it's done the same, because y's value is changed anyway. So it has the same as before, and this is still different. Okay.
It means equal. The equal here is like the same thing. It's not like a copy of the thing you are assigning to. It's like the same thing in the hardware.
Yeah, I mean, what I understand is that if you do this assignment, because y's value isn't changing, so it says, okay, I'm going to just tag this to x's address. But then, if you change the value for y to be distinct from x, then it just gives its own memory. It can be 2 times x or just some other number, right? I mean, I actually just 1 second. I'm really curious. Let's just do 3 and see what happens, right? I'm giving the same value, but this time explicitly. I don't know what it will do. No, see, it actually keeps it gives a different ID already.
So it's the same as pointers in C. Like it doesn't store value.
I don't want to go there. Okay. I know pointers. This is a different behavior. It's a feature of Python. So it looks like if you change it, if you assign it to have the same value even as x, it still changes the ID, right? So yeah.
If you change x and after you pointed y to x,
Yeah.
y keeps the previous value. is that? If it points to x, but then
Uh,
the value of x gets changed, y does not automatically change.
yeah, that's a good point. So let's see. So you want to see if x is changed, right? Say x is 2, and so you want to know what is x, y, and ID of x and y. Is that okay? So x is 2, and y is still 3, because I guess y is left alone when it was first made by pointing to x. But it also has changed the ID. Oh, interesting. Now it keeps the ID of y, which is the same as x, but changes the ID of x. But guys, I'm not saying I know why this is going on, but I think this is a weird thing about Python to be aware of. And I've gotten into so many issues not understanding this behavior, right? Because this is not like a standard C behavior. And I'm sure the Pythonistas will be like saying how great this is. This is some... Does anyone know why this is a great feature in Python?
I know that it's not always the case. In NumPy, for example, it's like C in NumPy. So if you assign and change the value inside,
that's good.
It's totally different. It will be changed.
Whatever,
The only issue is that if you recreate a new array, so if you say that x equal NumPy array whatever, and then y equal x, and y1 you change it, then x1 changes as well. But if you say y equals something else, then it separates the two.
Oh, right.
And if you want to take a copy, there is a method of NumPy dot copy.
Yeah. We'll get into dot copy for that. Well, anyway, this is all Pythonic magic, whatever you want to call this. You have to get used to this. Yeah, but it's not bad. I don't know what this was. Okay. Undo. So the next thing is truth statements and Boolean values. Right? So we want to basically assign truth values to statements like today is Friday, or 2 is greater than 1, 1 equals 1, and so on. So in SageMath, we can express statements, relations between numbers using these comparison operators or relational operators: less than, greater than, less than or equal to, greater than or equal to, is equal to, is not equal to. Okay, so these are your main ones. So if I ask, is 1 less than 1, that's false. Is 1 less than or equal to 1, that's true. And I can assign x value 1, y 2, and then ask is x equal to 2 by double equal to. So that will be false. You can also assign the output of expressions that return Boolean to variables. So here I'm creating a variable called my Boolean and assigning it this expression. Okay. I'm not sure if you really need the parentheses. Yeah, I don't, but I like it. Okay, and then you can ask what's the type of my Boolean. That's type bool. And this is just to check if two things are not equal. And we can print them. Yep, 1 is not equal to 2. Okay. So Booleans are very useful because you can keep the state of some program or some function, whether it returns the right answer using Booleans. Later on, you'll see Booleans are essentially the basic primitive behind what are called Bernoulli random variables, whether something happens or not. And okay, so yeah, let's do this. So try some strings. So let's say we say my string is I don't know, me, say Raz, And then I can ask if this is less than so. Okay, so it says ras is less than ras, right? So do you know what's going on? So ras is less than or equal to ras. So I think it's just doing. So if I do this ras b and ras a. Sorry, I think this will be false, right? What do you think? A. Because I think it's just using lexicographic comparison operators, right? So A, B, C, D, E, F, G is for dictionary ordering.
And what happened if you write cat?
Yeah, I knew you were going to say. I was about to say we should put a Chinese cat in there. I don't know. We can. I forgot I have to copy paste the Chinese cat though. I mean, I don't know what it'll do for lexicographic ordering. That's yeah, we want. Where was the assignment? So, yeah, I'm not really sure. Probably is using the integer order there. Decode UTF-8. Decode UTF-8. Not sure if we can just do this. Was it -8? Yeah, I don't know. I may have to assign this or something first. What am I doing? Oh, do I have to put it in a string? Yeah. Okay, so why? So then what do you want to do?
Is X bigger than
So okay. Well, so probably want yeah, so this is gonna be hard. Let's just concatenate to X something. No, I don't even know if this will be I'm not sure what type this will be. Yeah, so I have to really decode this again as a maybe if I add to y instead of x, it'll give me a Unicode string. Okay, so I concatenated 0. So now you want to, and that's also a Unicode string, so we can compare them, I guess. So you want to know y, is y less than z? Yes, it's true. Anyway. Okay, mathematical constants. So we have basic ones. So you don't want to use pi or e or capital I as variables that you assign other things to. That's a bad idea, right? Yeah.
Regarding the whole assignment business,
Yeah.
can I make you show one more thing?
Yeah.
So make a new cell somewhere.
Yeah. Yeah.
And then say x equals list of 1. Just a list containing just the number 1. No, just so brackets.
Oh, you want it to be like this, yeah?
Yeah.
Yeah.
And then y equals x.
Okay.
And then y brackets 0.
This.
Yeah.
Yeah.
Equals 5.
Yeah. Oh man.
Now print x.
Okay. So we're going to get into lists and copying and array and stuff soon, but I will do this. I won't.
Brackets.
Oh, is it some weird?
Print is a method, right? So
Y of 0 is
Yeah. So how do I
square.
do I square bracket? Yeah.
Sorry, I didn't see.
Yeah.
So now you see x has changed.
Mm-hmm.
And the reason is that x and y both reference a mutable object.
Yeah.
And then you change the mutable object.
Yeah.
When you do this for just a number,
Yeah.
numbers aren't mutable. So
Yeah.
when you change y, then you have to make it an entirely new object. Therefore, you're not referencing the same x anymore.
Yeah.
But with lists, the things containing lists are mutable. So when you do it like this, you can actually change the thing you're referencing to.
Yeah.
Therefore, you also change x when you do it.
Yeah. I mean, I don't.
It's something to keep in mind.
Yeah. I mean, I'm just sort of giving you. I mean, we will get into lists and making copies and things like this soon, but I'm also.
This should be the same. Right?
Yeah. So the IDs of this, but I guess that's because it's pointing to the head of the list or something. Yeah.
Sorry, not wrong.
Well, yeah. I mean, I Python behaves very, very differently with assignments, and yeah. So, but that still doesn't explain what the earlier behavior was. I just take it as granted. This is what it does. It gives you the ID, and what was this main thing? Yeah. So this is straight out of the Python tutorial. Yeah, it's one of these. So let's continue with this. So yeah, so pi and e and I, they all have some, they're already mathematical constants. So so you can have either lowercase I or capital I, both stand for the imaginary number, square root of -1. And so the nice thing is, because I'm putting .n, I'm getting the numerical approximation. If I just leave it as it is, and I evaluate this, e to the power of I times pi plus 1, this is the so-called Euler identity, it's 0. So that's a lot going on for nothing, right? It's pretty deep. Because I is already in the imaginary plane, right? So we only talked about real numbers, but then you move to a pair of numbers, and then these are called real axis and imaginary axis, and yeah. So this arithmetic is done there. So the moral here is don't use e, I, or pi to as variables. You can, but if you do, then you will lose these things. So it won't be there for you. So again, here's a bit more on number systems. So we already did this. So if I say x is 3.1, it's the Sage Real MPFR. But then if I want, this is the default floating point number in Sage, but this may be too heavy duty for some operations, and you may want just the standard one that Python uses, which is a float. So then you can do x's float of 3.1, so then it'll give you the standard Python floating point number, which I think is double precision number.
Yeah, the standard is
Yeah,
double.
Python is double, yeah, it's standard. And then this is so floor division. So division of operands where the result is the quotient, in which the digits after the decimal point are removed. So so here's floor division. So this will give us an error because the floor division is not defined for Sage real literals. So, but if you look at Python's double types by using float 3.5 and float 2.0, here floor division works. So, okay, so what else? Again, so we have this lightweight Python integer int. So, so if you do x equals int of 3, then we can get this type int, which is way lightweight than the Sage rings integer type, because that's this full-blown rings literal. So, yeah. So if we divide the Sage default integer 3 by the Sage default integer 2, you will get the rational 3/2. But then in Python, if you did the same, which is equivalent to doing int of 3 divided by int of 2 here in Sage, then you get the floor division. So it's the integer division. Okay, so what will this be? Int 7 over int 2. Is everyone awake? Okay. Okay, just remember that Sage is like another La La Land, really beautiful La La Land sitting on Python. So if you just do like 3/2, or you do some program where you're just using integers, and you don't really need in that program to use all the heavy-duty machinery of integer rings and things like this, then you will be wasting lots and lots of electricity. So what you should really do is cast it as an int if you're just doing integer operations and using int, or the same if you're doing something floating point in Sage Math, you write a little function. Then if you don't want to use the multi-precision floating point types, then just cast it as a float and just work with floats. And depending on your problem, this is something to be aware of. Okay, so we can always do help and look up. So we did this already. X is 3.55, xn digits equal 3, and so this is slight difference between digits and bits of precision. You can round x, okay, and find out what the dot string is for round. So you can get some other number to some digits of precision you want. Okay, so here is where I guess you would really want to dive into. So this is, I mean, I would bookmark your, not just this link, but the Python docs. So we're using Python 2. Most of Sage is on Python 2. Yeah, so you have your usual int, float, and then long is the long int and complex. Is long int, or is it some, I don't know. Yeah, long integer object. So this is basically to dive deeper into Python's integer types, and I guess okay, sets is our main next point. So I could have probably started with sets and then introduced numbers, but so this is a very foundational theory in modern maths, and So what is a set? A set is nothing but a collection of distinct objects, right? So it's just pretty much everything in probability and learning theory. A lot of it just builds on the notion of a set. So here is a set of polygons in an Euler diagram. So of course every pair of elements is distinguishable from one another, so it's a collection of distinct elements. Yeah, I think there was a big war going on between these guys. I forgot, is it Bertrand Russell who wanted to develop all of pure maths using sets? Yeah?
Yeah, there was a big war.
Yeah, I don't know. It was a anyway. There's yeah. So sets are very powerful. Let's look at some concrete examples. So in this little example here, I've just made a tiny set of two symbols. This star and circle. And then you use this notation to enclose elements of a set. So you use this curly bracket. Something like this. And then we can just give names to sets. So I don't know, I can call it A. So the convention is used to use capital letters in the beginning of the alphabet for sets. And then this is a trick question. Is this a set? Star, star, circle.
No.
Why isn't it a set?
State possible.
Yeah, because there are two stars that seem indistinguishable, right? So there's something called a multiset, which allows for multiple copies of the same element, but we won't go there. And yeah, you can just put some whatever you want. So then here is my symbol for empty set. So this is a very basic notion now. There's nothing here, some white space, right? So that's an empty set. And then these symbols are very important. So they're called belongs to or does not belong to. So I can say this element star belongs to the set A, right? I mean, I've drawn this perfectly, but it's the same thing. And I can say this element moon does not belong to A, right? Because there's no moon and half moon. So it looks like epsilon, but it's not. It's called belongs to symbol. Yeah. So 9 is not an element of the set, right? B is an element of the set, so on. So the next main notion is a subset. So we say a set C is a subset of a set D and write it like this. So so let's say, I don't know, I'll just do it like this. So I have an open circle and closed circle. This is a subset. I don't know if I use this or not. So, okay. So this set is a subset of this set because every element of this set is also an element of this. That's the definition of a subset. And if it's not the case, then you say it's not a subset and put a line through here. So if I had some person, third element, then this is not a subset, right? Because there's one element here which is not there. Okay, so that's basically basics of sets. Now we want to define, okay, what happened to union? Oh, that's crazy. Sorry. Oh, right, sorry, I'm doing operations now. Yeah, so then we can take two elements, two sets, and then define some operations on them. So the most basic operation is called the union, right, which is this U symbol. So I can say, we can remove this guy. So I can say the union of these two sets. Actually, let me put the guy back. I have three elements here and 4 elements here. So the union will be the set which contains every element of each of them, right? So it will be this guy. And then these are already there, so I don't want replicates, right? Set distinct elements. So this is the union of these two. Okay. So how you write this down is this way. So we should start writing and reading from set notations now. So the way you read that is A union B. So A union B is equal to the set of all x such that x is an element of A or x is an element of B. Right, so this is kind of how you, so it is the set of all, whatever this is, x, and then this symbol is such that this holds, right? So this basically is important notation. And then we can define intersections using the same notation, right? So you can say A intersection B is the set of all x such that x is in A and x is in B. Right? So if I define, this is the union, right? So if I want to define the intersection, so union is this. Let's say if I want to define the intersection, what will be the intersection of these two sets? Okay. Open circle and closed circle. Okay, so those are very basic operations. Okay, so then if you take the intersection of two sets that have nothing in common, you're going to get the empty set. Right? Now the other operation of interest is set difference. So it's this weird backslash. Right? So you say A set difference B, or A minus B, set minus B, is simply the set of all x such that x is in A and x is not in B. Right? So you can always throw Venn diagrams. So this is your A, it has a bunch of elements in it. And say this is B. So it's the set of all x such that x is in A but not in B. Oh, okay. Right? Okay, so there you go. So any set minus itself is nothing. And then equality itself is defined, right? So I mean, this is all like, if you're super crazy formal, you put colon here because this is the definition. So we're abusing a lot of stuff here. So we say two sets are equal, A equals B, if and only if. So this is just a logical notation for if and only if, or equivalent to. So A is equal to the set B if A is a subset of B and B is a subset of A. So yeah, two sets are equal if everything in A is in B and everything in B is in A. Right? Yeah. And then we say two sets are disjoint if the intersection is empty. So this is nothing in common. So A intersection B is empty. So that's what this word disjoint means. Yeah, so this is if and only if, or IFF. Oh, same as equivalent to. And then finally, we have this notion of a universal set. So suppose there is a set, usually in probability, we call it capital omega. It's, so let's say the universe. So given some notion of the universe, omega, it's a set. Then what we can define as some other set A, let's say is a subset of omega. Then A complement is simply everything in the universe that's not in A. Okay, so that's the definition of A complement. You just put a little C there above A here. And formally, it's a set of all X that's in the universe but not in A. And yeah, so there's a lot of going on here, right? So you're given a universe, so this should be there. And the A you're after, whose complement you're after, itself should be a subset of omega, right? And only then this is well defined. Okay, so that's basically set theory in like 10 minutes. And that's what we will be building on top of for probability theory. Okay. Yeah, this is just some, I don't know if it still works. This is for kids, right? But it's cute. So you can put any sets you want here, and you should see an interactive Venn diagram. Yeah. So little a is in all four. It's an X, Y, and Z, and yeah. So it's useful to think about Venn diagrams playing with sets. Okay, how do we create and manipulate sets in Sage? So here is a list. So we'll learn about lists first. So this is what Don wanted me to do earlier. So my list is, yeah. Oh, sorry. Yeah, thanks. Yeah, so my list is 1, 2, 3, 4. And I'm going to print my list and then find out my type. So it's a type list. So remember I said list is like this ultra basic data structure, and list processing is this programming language that's quite basic. And you can use lists to create lots of other structures in computer science. So here is how we create a set with this lowercase set. Okay. So this will create a set. It'll take as an argument this list 1, 2, 3, 4, and if you put that list inside the parentheses for set, it'll create this nice set-looking thing, right? And I can ask what is the type of X. That'll be a type set. Yeah, so this is a specialized data type. So let's see what the Python docs tell us. So we have various data types, list. Later on, we'll see dict for dictionaries and sets, and there are immutable versions called frozen sets. And we already saw str, so strings are actually another container, and another specialized sequential container. So these are built-in things. So you can ask things like 4 in X. So is 4 an element of X? And that's true. Is 5 an element of X? and that's false. I can create another set called y. It's a set containing two elements, 1 and 2. And I can again ask, is 4 not in y? That's true. 4 does not belong to y. And I can ask 1 not in y. That's false because 1 is in y. Now I can start adding elements to set. This is like a union operation, but it's implemented using this .add method. So I can add 5 to x, and I get set 1, 2, 3, 4, 5 now. I can, if I try to add an element that's already there, the set implementation makes sure that it doesn't make double copies, right? So it leaves x alone. So here's a little example. You want to try to make the set z as 4, 5, 6, 7. And then check if 4 is in z.
What if I want to make the set of the array 4 to 7 instead?
The array, we haven't seen arrays yet. We only have lists. So
but in some sense, you were using it because you were using set of and then the array 1, 2, 3, 4.
Oh yeah, the list 1, 2, 3, 4.
I wanted the set which was containing that array and not the integers.
Okay, so
because actually I thought
you mean this one right here?
Yeah. If I want to have a set containing of the array 1, 2, 3, 4.
Oh, I see. Okay.
Because I actually sort of thought I would get that from
No, so I mean we can get into that, but I mean, first of all, there are things called arrays that are not lists in set, so we should call this a list.
Okay.
So maybe what you're asking is you want a set that's made of a list of lists. So this is a list containing a list. I don't know. No, that's a type error. So
you don't have to go there. Actually,
I
was confused because I thought that was what we were going to get when I saw the expression.
No, I mean I'm just giving it 4 elements. Yeah, so I don't know what will happen. So I guess if I make a list containing, I have no idea what will happen, right? I'm just so this is a list of so yeah, this unhashable list. Yeah, so you need it to be a hashable type, right? So this is yeah, so this, I know what's going on. So basically you have to, okay, you're just jumping ahead of me. So you need to know, I think this will work. Yeah, so okay, just wait, we'll get there. So it's working because now I'm giving it a list of immutables, and this immutable is now a tuple, which you'll see soon. So if I give it a list of tuples, it's fine. And what I gave it initially was a list of integers, which are fine as well, they're littles. So, but if I give it a list of lists, it's not happy because, you know, the elements of a list of list is a list, and the list itself is mutable, and set needs immutables, or whatever it's called, hashables or something, because it uses some hash thing under the hood. All right, let's, I think I get into all this here at some point. So let's see. Right.
Hey, Ross?
Yeah.
So the set function you have there,
Yeah.
what it does is it takes an iterable,
Yeah.
right, and it converts it into a set. So it doesn't take some object and put it inside a set. It takes an iterable and converts it into a set. It will take a list. Strip out sort of the brackets. And put the other brackets on.
That's right. That's right.
List and converts it into a set.
And then when I was seeing the error message, when I did the list of lists, it said that the elements should be hashable or whatever.
Because you didn't provide it with an iterable data type.
So I just realized that as I tried.
Over and put each element in that iterable thing into a set.
Yeah, but the elements of the iterable thing should be hashable was the error that I got. That's why I had to put a list of tuples, not a list of lists, right? I mean, you can try that. I just tried that before. So if you do a list of lists, let's not get into this, right? Because I have like a whole 1 hour of like mutables and immutables and hashables, all of this coming at you. So we're just Yeah, so we need a list of certain kinds of objects. So let's continue with this. So if you type in z equals 4, 5, 6, 7, and then check if 4 is in z, it should be straightforward, right? So let's do this. Z equals set of 1, 2, 4, 5, 6, 7, and then I want to see 4 in Z. Okay, so if I can, instead of putting a list, if I see if I can put a, so I can also give it a tuple, but I cannot give it a tuple containing lists. Yeah, this is what I got, unhashable type list, which is an element of the tuple or a list. All right. Yeah, so I'm not like a expert in anything, So there's definitely going to be problems. Sorry?
It's kind of got to do with what you said about immutable.
Yeah.
Like simplifying, a set can only contain immutable objects.
Yeah.
And a list is not an immutable object. Therefore you can't put a list in
And I think even lower level, it needs that because it uses a hash implementation to maintain the objects, the structure. Okay, good. So some of this stuff, like if some people are like, oh my god, what are these guys babbling? It's good to know. Good to know that, it makes sense, right? What we're talking about. And if it doesn't, just hold your horses. It'll make sense. So here is subset. So now I can also do like, so my x is 1, 2, 3, 4, and my y is 1 and 2. And then I can ask, with this less than or equal to, this operation, less than or equal to on sets, is overloaded as subset. So I can ask, is x a subset of, or y a subset of x? And then this evaluates to the Boolean true. Yes. In this case, 1 and 2 is a subset of 1, 2, 3, 4. Now, this is called a proper subset, so we didn't see this in the definitions. So we say, this is why I, so there's many ways of writing this. So I put subset here, right? So A is a subset of B. So one way to say that A is a proper subset of B is to put an equal to here and say not equal to. So A is a proper subset of B if every so there is at least one element in X that is not in Y. So that will be a proper superset and a proper subset. Okay, so here X is not a proper subset of itself. X is a proper superset of Y, and X is a proper superset of itself. It's not true. Okay. So we don't really need to know those things too much, but I just threw it there because they're implemented in the methods. So here is an intersection operation. You can use the and symbol for intersection. And then the pipe symbol is also same as the union operation. So I can take the intersection of x and y and take the union of x and y using the pipes. That returns the union set. Set difference is implemented as a minus operation. And I have no idea what star does. It probably does Cartesian product. I have no idea. Anyway, you guys can play it out, and then there is the Python docs. You can knock yourself out. So this is just a little example. I'm going to define a set called fruit, which is a set of these 3 strings, orange, banana, and apple. And then I have another set called colors, which is a set of red, green, blue, orange. And then I'm simply just doing the same thing. Fruit intersection colors is orange. Fruit union colors is blue, green, apple, orange, banana, red. And the set minus is banana and apple. And colors minus fruit is blue, green, red. Okay. Yeah.
Question for, why do we want to use set instead of list?
Because probability theory is built on sets. So I want you to basically be comfortable with set operations. So later on we just define some other objects. We can take a set of them and take another set of them and do operations with them.
Also, this list have an order and sets doesn't.
Yeah, that's right. So lists have an order, they have a sequential order. Sets, well, they kind of have a hash order, but conceptually they're not ordered. They're just a collection of distinct elements. Yeah, I mean, the point is this, right? So if I create my set here and ask what are all the operations available for me, so I can, do quite a few things. And we want to sort of play in this generality because, with the tools you guys will get eventually, you should be able to create your own set and create operations on them, build models with them. So, okay, so there are in fact two ways to make sets in Sage Math. We've so far used the Python set. So that's the one here. And this is where you would dive deeper into like various operations on them. Yeah. Right, so this is just, you're only being shown a very tiny fraction of this. But the other way to do it is to use Sage Math reference on sets. Right. So if I open this, just like Sage Math has floats, has multi-precision floating point reals, and Python has floats, this is Sage Math sets. Okay. So they are slightly different. Okay, so here is my set that we were just doing in Python. And if I ask type of X, it was the Python set. So here's another set, you see. So you see the difference? This looks the same, but then you ask what is another X? It's the Sage set object enumerated with category. So do you see what the difference is? It's capital S, right? Yeah. So, okay, that's what that calls the, yeah, I'm just going to leave it at that. It's more mathematical, but all these operations will work on the Sage set as well, and a lot more. So if you want to find out all the other things that are there for another X, this is the Sage Math set. It has a lot more operations built on it. Okay. Now here is a frozen set, so this is useful if you don't want it to change. You want it to be immutable. So you cannot add an element to a frozen set, for example, because it's frozen. So what's really under the sets hood? So this is, so basically, the keys are the elements in the set, and they're actually unordered in a mathematical sense, but they're actually kept in a hash table inside the set. Okay. And if you don't know what hash tables are, then just look it up here. So hash tables are a very fundamental data structure. So it uses a hash function to compute an index into an array of buckets or slots from which the desired value can be found. So it's that's what sets are actually using inside to represent elements. Okay, so that's all about sets. So now let's look at the third notebook. So we're sort of moving into the next layer, which is maps, functions, collections, and probability. Okay, so what are maps? Maps are really sets as well, right? They're sort of special kinds of sets of ordered pairs. But it's easier to just directly think of them this. So you can have like two ways of thinking about a function. So you can think of a function f as some kind of a black box that takes as input some x values, and the x values usually live in something called the domain, right? Here, these are the x values, and then it will do some magic to it and then output f of x, the corresponding value. So in this example to the right, the function is the color of function. So the input is the red triangle, and it says the color is red. And the red square, the color is also red. Right, so this is just telling you what the colors are. And yeah, that's basically the function. And formally, it's a relation, which is the I forgot, what is the definition of relation now? Relation. What's a function? A function is a relation.
No, well, that's, yeah.
Yeah. Yeah, it's a collection of ordered pairs of elements. Yeah.
Generally, a relation is just a subset of the Cartesian product. Yeah. A function is a subset of the Cartesian product and some extra conditions.
Yeah, yeah. So anyway, so basically, yeah, you can think of let's see, and we'll kind of dig into this a little bit because it's just the same thing. So we have some set called the domain, which is where the inputs live, and another set called the codomain or the range, where the outputs live. And so this is domain, and this is codomain or range. And let's say here's little x, little y, little z, and let's say this is little a, little b. Okay, so I think so if I enumerate all the ordered pairs, right, where the first element is here and the second element is there, I get this, right? X comma a, x comma b, y comma a, y comma b, and then z comma a, z comma b, right? So this is a Cartesian product of all possible pairings between this. So this itself is in a set, right? Okay. So and then I can restrict this possible ordered pairs. I can say I only want some specific subset of this. So function is so this is basically a relation. Subsets of that set is a relation, and then a function is a specific extra condition on that relation. So what are the conditions? The map or function associates each element of the domain with exactly one element in the range. So so I can go like this. X goes to A, but I cannot do this. X also goes to B, right? That's not allowed in a function. So I usually think of sons and fathers, right? So domain is my set of sons, and this is my set of fathers, and every son has to have a father, right? So every element here has some image. So let's say do this and do that. Okay. I can also have a sonless father, but I cannot have a fatherless son. Right? And every son has only one father, so we don't do any artificial crossing of the Y chromosomes, right? So there's no immaculate conception. There's only, every son has a father. So it's actually a very easy way to remember conditions posed by a function. Okay, so yeah, more than one distinct element in the domain can be associated with the same element in the range. Yeah, there can be two brothers who have the same father, and not every element in the range needs to be mapped. So you can have childless fathers. So this is just with I have two daughters named Anu and Ashu, and Jenny was my teaching assistant in New Zealand a long time ago. She's got a job and everything now. So she and Kathy are daughters of Jonathan, right? And Fred is a man with no daughter. This is exactly the same. Yeah, find father's map, right? So you have daughters to fathers. This is the domain and range. And we can think of find father's map as the name of our function. And this is our notation. We put a colon and say what the domain set is. And then we put this arrow and say what the range set is. Right? So here, this function, if we call this function f, then let's say we call this set capital A and call this set capital B. Then we just say f as a function that goes from A, and then we put this arrow. Okay, so yeah. So then you can say my f of x is A, right, in this example. My f of y is B, and my f of z is A. Okay? Those are standard notations. And yeah, so the other way of thinking about this as key value pairs, especially when this is finite and small, we can now take each element, as the key, and this value takes its image as the value. So and then we can start thinking of them as dictionaries in Python, right? So a function that has not too many possibilities can be just seen as a key value pair or a dictionary in Sage. So here is an example of not a function, right? Because Anu cannot have both Raz and Jonathan as her set of fathers. Okay, so this is essentially the formalism. So f is a function that goes from map bbx to y. It maps each element of x, each element lowercase x in the domain to exactly one element in y. And as I said, it's equivalent to this set of ordered pairs. So I can say my function is nothing but the set of all x comma f of x, right? Oops, x comma f of x, these ordered pairs, such that x is an element of my, so I'll make this x now, this y now, and y, f of x is an element of map BBY. So later on, you're going to see three levels of notation. So you'll have x. X can be an element of the set map BBX. And then we're going to introduce soon capital X as a random variable, right? So little x will be realizations of this random variable capital X. And so we will at least need three forms. Okay, then maybe the most important concept before lunch is this, the preimage or inverse image of a function. And yeah, so if you get this, then probability theory is pretty much all about preimages and images, right? So the inverse image of a function f goes from, what did I do here? Oh yeah. So this is a Canute notation, so I don't know, a lot of people don't like this, but I like it. So typically, some of the textbooks will just put f to the power of -1, but I don't like that because something to the power of -1, as Knut nicely argues in his Art of Computer Programming, also stands for 1 over f. So Knut suggests using this notation, f to the -1 enclosed in square brackets. I use it just because it's easy. So what is this? So my f goes from x to y, right? So suppose I have a function f that goes from domain x to some codomain or range y. Now, given that, I want to, so x, just visualize x as some bunch of objects that are here, and y as some other bunch of objects, distinct elements, these are sets. So f goes in this direction, f inverse goes in this direction. Okay, and what is f inverse doing? It can be applied to, so I can say f inverse of a particular element y, let's say this particular one is lowercase y, generically, is now the set of all x in the domain such that f of x equals y. So it's this definition, right? So this guy goes in the other direction, right? But yeah, it's saying what? Give me all the x's. So you shouldn't. It goes in the other direction. But let's say this particular value of x went to this y, this also went to this y, and everybody else went somewhere else. Okay. Then the inverse image of this y is just these two guys, right? So that's basically inverse image, yeah?
So it's not a function of the preimage.
No, right? Preimage need not be a function. That's kind of the point. Yeah, we want it to be general. So it's just, and in fact, this y doesn't have to be just a point. You know, so I can say, I can also define f inverse of some arbitrary set B, right? So B is just some set, bunch of guys, right? So I can define the preimage of that to be, what will it be? Can you try to? So it'll be a bunch of x's, right, that live in the domain, right? Because it'll be a bunch of points here. So that part is still true. The set of all x in BDX such that what? Such that f of x equal to b? Yeah, good. It's an element of b. So now we're like really pumping, right? We just set operations. So basically that's the primitive. This is essentially what's under the hood for probability theory and events and so on. We'll get there quite soon. Yeah, so here's, so inverse image takes subsets in y and returns subsets in x. That's it, right? So B is some, so for any B, that's a subset of y, right? I have this well defined. So now, yeah, I should have really defined the more general thing here. Okay, so I don't know, is this LaTeX? Oh yeah, it is. So you know what I should really do is this, right? So I should say more generally. Right, so f inverse of minus 1 of some b is equal to set of all x such that f of x set of all x in b dx such that f of x is in b. Okay. Any b, oops, that's the subset of, is that right? Ooh, subset of y. Yeah. That's correct. Okay, so that's probably what I want, right? That's the more general argument. Okay. Yeah, so the find fathers map inverse at Raz is Anu and Ashu, and find fathers map inverse at Jonathan is Jenny and Kathy. And now we can just take the same idea and drop into number systems, right? So we can take sort of f of x equals x squared, the quadratic function on the real line. So here, the version 1 of this function is going to have a finite domain, say only 5 elements. So we can take minus 2, minus 1, 0, 1, and 2, and then ask what is f of x equals x squared. So clearly the negative ones get squared and land in 2 and 4, or 1 and 4. And the range is 0, 1, 2, 3, 4, and so some of them are not mapped, but that's okay. Okay, so we can then see this as the following set of ordered pairs: minus 2 goes to 4, minus 1 to 1, 0 to 0, 1 to 1, 2 to 4. And yeah, that's our first numerical example. Now in the version 2, we are now saying let the domain be the set of integers. So now we're going to map it over the entire set of integers, countably infinite set. And then that's going to give me 0, 1, 2, 3 upon squaring, right? Or say that's my domain. And it's the same exact idea, it carries through. But of course, we cannot implement it as a dictionary now, right? I mean, explicitly as a dictionary. We can do it lazily as a dictionary. So the same way if x squared is the function, but our domain and range are reals. So then we are back to this familiar picture, right, of the quadratic map. So to implement these notions in the machine, we will need to think about functions as procedures. That's kind of our next main stop. I guess it's already lunchtime. So did you guys... I don't know what's happening to my URL thing. So did you guys bring lunch? Okay. You have to go downtown. I hope something is open downtown. Yeah, it should be. Yeah, so I think 1.5 hours should be enough, right? Yeah. Okay. So let's meet after lunch. I don't know. I hope maybe this is going way too slow. But well, like Marina needs it, so it'll pick up the pace. I think. I hope. Yeah.
So this would be
Interesting.